Okay. Anything you say will be. The people who are on Zoom, if your camera is on, you might pop up in the video. So if you don't want to pop up in the video, apparently 400 of you people watched last time, which is very scary and concerning to me. Have your cameras off. Yay. Fun. Okay. Ben, for some reason, Zoom has picked you to be the thing everyone sees. So make sure your camera's off. I don't know how to change that, but that's what we're going to see for now. Okay, now it's Dylan. Cool. Most of you guys thought it like fun times. Okay. So, yeah, I know. There's no way they can be on there because I have to teach you guys that stuff in lab this week and next week. That's buffers. But everyone? Everyone sign this? Cool. Oh, more people. Yay. So Zoomies, if you have questions, feel free to do it. You leaving already? Yeah. Okay. So good. I'll record it. I'll upload it later. I didn't start yet. I feel bad. No, I can get that stuff later. I have access to that stuff. I have too much power. It's weird. Yeah, it's concerning. I can see where you live, your social security numbers, or anything you give to the school. I have access to it. I'm not going to do anything with it. Most of you guys are broke college students. I'm a broke college student. I would not. Why would I take money from the little money you guys have? You guys are in debt right now. There's nothing to take from you guys. As this is being recorded, this will be fun. No, I have my own debt to pay back. No, thank you. Wow, more people come on in. No, don't remove Alex. No, 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 no. Okay. So as that's going around, so I know the quizzes have been rough, so we're gonna go over this stuff. The best way to study for this stuff, as it doesn't seem as important, is the practice questions. Just go right there. So, well, I have a comment already, wow. Hello. That's my meeting password. Made it nice and simple for people. Oh, already got more people coming in. Okay. More people on Zoom. There is to be in the classroom. Fun. Okay. So I know the chapter 12, 13, and 14 practice question was rougher than the 15 and 16 one. Okay. The only thing I can think of is that this one will be more practical questions, more thinking questions like that, while chapters 15 and 16 will be more the mathematical ones. Because again, chapters 13 and 14 are going to have to do with Chatier's principle, which is heavily tested for those units, right? Very, very easy way of doing it.
What? Yeah.
Oh, you guys are, like, everyone can hear you. So.
Really unfortunate.
Cool. You guys can speak, just know that everyone can hear you. And it will come back up on the recording I'll post later. Because I do not have time to edit 3-hour-long videos. Cool. So let's start with chapter 13 and 14. I'll move on. I was kind of busy this week, today. A lot of my things in my house are breaking, so a lot of drives down to Home Depot and Lowe's to get fixed things. So I didn't have time to get extra questions or make extra questions for this. So the only thing we have are the practice questions. So if that doesn't sound appealing to you, I am sorry, but they're good practice anyway. Okay. So, what relationship of reactions rates is correct in the following things? So, you guys need to know that right now, chapters 15 and 16 has to do with K, correct? And K is equal to what? Products Overreactance. Every time I do something, more people in the waiting room. Cool. The product's overreactance, right? You can have Ka, which is the concentration for an acid, rate constant. Rate constant for a base. Rate constant for some concentration. Rate constant for pressures, and so forth, right? However, if I'm dealing with reaction rates, like in question 1 right here, it's not products over reactants. It's products minus reactants. So I'm trying to figure out the reaction rates. Does that make sense? I'm trying to figure out how much reactants I am making per product, basically. How fast it's going. So, what you're going to do is you're going to take your reactions, your products, minus your reactants. I can zoom in, yes. I have to get this in. There we go, one at a time. So, first steps first, before you do anything, always look. There are 2 types of elemental forms we don't care about. What are they? Well, we care about aqueous. We like aqueous. We don't like liquids and solids. Those are no-nos. They don't react to anything. They're boring. An aqueous solution is a liquid solution with something inside of it, right? So like, for example, salt water is an aqueous solution, but pure water itself is a liquid, right? So if you're looking at all this stuff, we have aqueous and gas solutions, which means everything should be in there theoretically speaking, right? So, compare your products and reactants. Okay, second thing I want you guys to look at, or know, reactants, are they used up or are they produced? They're used up, right? Which means they go down over time. So this side's gonna be negative. What's this side over here gonna be? Positive. Let's look at this. NO is a reactant, correct? It's negative. That's good. Oxygen though, that's also a reactant. Reactants cannot equal reactants. That's a no-no, right? Oxygen nitrate is not making oxygen in this equation, correct? So A is wrong. Oh, there we go. Okay. CO, nitrate, is saying it makes Na2, NaO2. That's correct. Reactants are negative. Product should be positive. Oh, that's a no-no. So C is wrong. Does that make sense? Okay. NaO2 is equal to CO2. Well, that's correct. That's good. I like this, right? However, product. Nope. O2, reactant, not negative. Answer is B. So the reason why you're picking B, first off, you have a product equal reactant, which is the same thing as a reactant equal to product, right? Goes both ways. Because as you guys know, sometimes a chemical arrow goes both ways even when it's not shown. It's always both ways from now on out. Even though it doesn't say so, it is a little bit, right? The reason this 4 is here because it takes 4 oxygen to make 1 NaO2. Does that make sense? If you wanted the other way around, it would take 1/4 NaNO2 to make 1 oxygen, right? That's how you would do it the other way too. Does that kind of make sense? That would be negative. Okay. I do question stuff like that with 1. If you're asking relationship between reaction rates. Okay. So now we have to figure out, given a reaction, how to figure out reaction rates. So here's a reaction given, right? Products and reactants. And I'm told the reaction rate for Fe2, no, F2 Okay. Now the zoomies have outnumbered you guys, which is even scarier. Okay. So, what's happening here is I want to figure out how much products I make given the reactants. Correct? So what is the value of this guy? Well, he theoretically, BrF3, 2 is equal to 3F2, right? Treat this guy kind of like an X value. Divide by 2. Cancel that out, right? So BrF3, bromine fluoride, trifluoride, is equal to 3 over 2 concentration of F2. So just plug F2 in, and you should get your answer, which is D. Now that kind of makes sense why I did that. Because I don't care about this guy at all, right? And for every 3 of these guys, I make 2 of these guys. But if you notice, what I'm asked to solve does not have the molar constants with it, correct? It's just asking for the thing itself by itself. So how much of one of those do I make, theoretically speaking, right? Another way of looking at it is I could just times 2.4 times 3 times 3 to figure it, then divide by 2 to figure how much I get one of these. This is your practice question 1. You should be able to have it. You guys should have access to this. Should be in your Loud Cloud. Okay, so rate law. Rate law, rate law, rate law. You guys have lab stuff on this, and you guys have been quizzed on this before. This will pop up again. Number 3 is pretty easy. Those of you who are taking calculus right now or pre-calc, or those of you taking college algebra before, when multiplying exponents by each other, what do? You add them. So what is 2 plus 0? 2 minus 1. 3 plus 0. 1 plus 3. 3 minus 1. Which one's equal to 3? That guy. So the overall reaction order of this guy is 3rd order, right? However, if I ask just for A, what order is just A in? It's not that hot out. So A is in the 3rd order, B is in the 1st order, but overall the reaction is 3. Because if something's in the 0 order, it really doesn't matter at all, right? Because what's something to the 0 power? 1, right? Like 49 to the to the 0 power is equal to 1. Well, I'm a person. I have a name, Ben. Ben, 22102, North Lecture Hall. Yeah. 3.6? 3.6? You get trouble last time. Give me a second. Could be wrong. Oh, Mattis wants to join. Cool. Yes, so you're correct to get 3.6. 2.4 times 10 to the negative 4th. You guys have an answer key to this one, don't you? Yeah, it's 1.6. So what he did instead, and it could be an issue with the key. Yep, that's correct, Matthew. I'd like to write. There we go. I can write now. Okay. is 2/3 times 2.4 is how you get the 4.6. So do 2/3 first and then times 2.4. Why 2/3? Because it's 2/3 because of 2/3. Because it takes 2/3s to make that. Oh, that's a good question. Okay, thank you. Okay, going back to a couple months ago. So the reason it's 2/3, I messed up talking about number 2 real quick. So the reason it's 2/3, right, is because going like the one back up here, right? How B, the O is the 4th power, right? So you're gonna move this one over to this one. So it's 2/3, that's why. Okay. Nice, nice, nice. Okay. If you're given a rate law or rate reaction, for example, like this guy, and you're told to plug in concentrations, you just plug them in. Because brackets are equal to what? Concentration, which is also equal to what? Molarity is also equal to moles or liters. They're all the same thing. Cool. So plug those numbers in. For example, plug 4 into D. So 1/4 to the 1/2 power is just basically square rooting D, right? And that will not do what number 4 wants. Before once, it's saying to double it, which is not true. The one that works out is C. I'm not gonna do all the work because we have to go through 100 problems, and last time it took me 3 hours to go through 50 problems each. So unless you guys wanna be here for 6 hours, which would be midnight, I'm guessing you guys don't wanna be here by then. So I'm not gonna do all the problems. The other videos I have up that have that, I'm just going over the ones I think are gonna be on the test. Again, I've not seen the test. I'm not a chemistry IA. Haven't been one in about a year, so they've changed things up. But the ones I know on my tests were stuff like this and ones further onwards. If ones that popped up on your quiz are on here, let me know. We go over the ones in details. No, we're just gonna go kind of quickly by. We have a lot to go by. Okay. So, rate law. What is true? So, how do you determine rate law? How do you guys experimentally determine rate law? You use this thing, right? This matrix right here. Correct? You guys kind of remember this? Been in hot six, you guys seen this? What's the difference between trial 1 and trial 2? What is changing? Initial rate of what? Of hydrogen gas, right? What's happening to the rate of NO? Nothing, it's staying the same, right? So we need a dependent and independent variable, correct? So you go back up to number 5. All right? You're going to need one in which the initial rates of one concentration rate is varied, or the one is unchanged to determine the values of the exponents for the rate law. That's what C says. C tells us how we solve for it. It just puts it into words instead of pictures and such. Kind of make sense? Cool. So let's solve number 6. So how would I go about this? What I would do first, if I were you guys, is I would label these as 1, 2, 3, 4, 5, 6. So I know how many trials I'm dealing with, right? Now I need to pick 2 trials in which the concentration of hydrogen gas is changing, while the concentration of nitrite or NO gas is staying the same, right? That happens in the first 3 trials. The last 3 trials, hydrogen gas is staying the same, while nitrite gas is changing. So, which one do you guys want to experiment with and play with? Which trials? 1 and 2. So always put the newer trial over the first trial, right? So 2 over 1, 6 over 6 is equal to rate over rate, 20 over 40. So what's 6 over 6? That's 1, right? Let's change colors. Let's go black. So what's 2 over 1? What's 40 over 20? So put an exponent here, x, y, whatever exponent you want, right? So how do I make this statement true? How do I make x true? What does x have to be to make 2 equal 2? 1. So hydrogen is to the first power. Does that kind of make sense what I did? That's how you're going to handle rate and determine the rate law, initial concentrations, initial rates of stuff. Okay. Next up is for nitrite. What 2 trials did I do to keep nitrite the same but make hydrogen gas, or to make nitrite different, hydrogen gas the same? What 2 trials do you always want me to pick? 5 and 4? Cool, 5 and 4. So 18 over 18 is what? 1. Okay. Zoomies, you can talk at any time and ask questions. It's just going to be heard by everyone. So if that scares you, I apologize. Text and chat. Okay. So 1 times 2 over 1 is equal to 40 over 10. So what's 2 divided by 1? 2y, just make it different than 2x, is equal to 40 divided by 10, which is what? 4. I'm like, why am I getting blizzard insurance? What? Whatever. Okay, what does y have to be? So H squared, or hydrogen gas, is in first order. Nitrite, NO, is in second order. Which one is that? Which one is hydrogen gas in first order, nitrite in second order? B is the answer. Makes sense. Does it make sense that we solved this one? Now, one of the other practice questions exactly like this one. So we're going to skip that when we come to it because it's exactly the same thing. I think it's like question 23 or something like that. It's exactly the same. Okay. You will definitely need to know how to do this. This will probably pop up on your tests or exam. Number 6 and ones like it will pop up because we'll see we'll do ones like number 6 a lot. And ones you do a lot will pop up. Now, I do feel bad because I did tell you guys last time that one like number 7 would not pop up in your test. And guess what? It did. I don't know why. They make you do the thing for rate order. Yeah, I know. Langley's talked to me about it. It's annoying. Okay. So, rate is equal to what, guys? K, right? There's K right there too. So, the first order with respect to CO and third order with respect to Cl2. If the units for the rates are mm, right, concentration per minute, what are the units of the rate constants? So, CO doesn't really have anything, right? It's first order. That is not going to affect us at all, correct? So we have something that's concentrations of 1, and this guy right here, Cl2, the concentration to 3 over 2. Now, because CO is 1, I really don't care about it, right? It's pretty easy to get rid of. So I'm not going to care about it too much. This guy is the weird one I don't like because he has this 3 over 2. Correct? The whole point for the unit for K is to make sure that everything kind of equals out, correct? Because K really doesn't have too many units itself, right? K doesn't have units. It's just this per whatever. So, how do I get that by itself? Well, K is like this, right? So what is rate going to equal? Well, MM, so I put M, min, right, over big M, over little m. Does that cancel out? Theoretically speaking. Yes. Okay, that cancels out. That's why it's over 1 here. That kind of makes some sense? Min per that. Because that's units for rate, right? I want K to cancel everything out, right? Because K doesn't have units. Or K's units is make sure nothing has units, right? So K will equal anything that will cancel everything else out. So that's why it's me 1 over that, because I'm already giving the rate in the units, correct? And eliminates A and D. Now, how do I get rid of these 3 over 2? If I have exponents like 2 squared over 4 squared, when you just, what's the rule when you're dividing by exponents? You subtract them. So how do I get 3 over 2 by itself, or get rid of 3 over 2? What do? I put the same number on the bottom, correct? That's why it's E. That kind of makes some sense? Yes or no? Because I want to get rid of 3 over 2. Well, Nicole was in, but now Nicole's not. Hey, one of the Zoomies. I'm going to make you co-host. Your job is to let people in for me because I am too slow. So I'm going to make a couple of you that I trust co-host. No pressure. It's the ones that make co-hosts all the time.
Shane, I'm driving right now.
Why are you driving?
Because I'm coming from class.
Fine. Hello. Come sit down. You're good. I'm not going to yell at you guys. Okay. Well, Liam, Savannah, you're co-host. If people come in, let them in. That's your job. Just hit the emit button. Do not remove them because they'll get kicked permanently. And that would be awkward. Okay. That's how you do number 7. I know it kind of doesn't make sense, but so you have to rationally think about it. You want basically the units for the rate constant to make sure everything else cancels out. That's kind of how you do it. So I didn't really talk about it too much. I didn't think they would test about it. But this year, I guess they are, which is very annoying. Okay. Number 8. So the reaction D is products is first order. So what order am I dealing with? First, rate constant. What's the rate constant? Okay. Good. The initial concentration is 3. The final concentration is what? Is it given? That's my X value after 2.5 hours. So these should be given to you. Make sure you ask your professors about them, though. I know some of you guys didn't have access to them, and it sucks. These should be given to you. You should not need to know how to memorize these. These should be given to you. Make sure you can ask professor for the test, though, if these are given to you and how to get them for the test. Okay? So we're going to use first order, which is natural log of final concentration is equal to negative KT plus the initial log of that concentration. Cool. So ln of A is equal to negative KT plus ln of A. Okay. So plug your answers in. I like these problems because you have to figure out what you're looking for. and plug the rest in. No? Do I have it? Do I see anything up there? Yes, you actually do. I messed up because this right here is in seconds. Yes, the units is in seconds. So we got to change it to 2.5 seconds. So 2.5 hours. All right. And that is 1 minute. Oh, yeah. 60 minutes over 1 hour. 60 seconds to 1 minute. Cancel, 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 cancel. So 2.5 times 60 times 60 is what? 9,000. See, 5,000? Oh, 9,000. Okay. Okay. Oops. So we have 9,000 seconds. Okay. So Ln of final concentration is, I don't know. I plug that in, is equal to negative 2.7 times 10 to the negative fourth. That is times 9,000 seconds plus the initial concentration of 3. So solve for everything. Negative 2.7 times 10 to the negative fourth times 9,000. The ln of 3. So that plus that. Cool. So e to that number. Okay. So you guys want to solve this step by step? You guys can do it by yourself. What do you guys want? Step by step? Cool. So first, solve for that guy. So what's negative 2.7 times 10 to the negative fourth times 9,000? Negative 2.43. Changing colors up a little bit. Next, natural log of that guy. What's natural log of 3? .09, or roughly around there. So negative 2.43 plus 1.09 gives you what? Negative 1.33. Bring this down. Ln of x is equal to that. How do you get rid of ln? What do you do? Huh? E power, right? Boom, cancel that out. Put that to that. What do you guys get? 0.26 concentration. Does that make sense? I can almost guarantee you a problem like number 8 will probably be on the test, because questions like this pop up a lot in the practice test.
How do you know which?
What, ln?
How do you know which one to take?
Because the equation has this, right? So what's this 0 right here mean? That's not, it means initial, right? So your initial concentration is 3. So that means it initially goes into here. Your final concentration is there. That kind of makes sense? Usually your initial should be higher than your final, right? That's why our K value is negative, because we're saying the reactants are being used up. That makes sense. Why are we doing it right there? Whoa.
If our initial is higher than the final, that means they're wrong.
Probably yes. Most likely. So. Okay. Cool, cool. Okay. Going down to number 9. So graphs are always fun, and graphs are usually thrown into exams because they're a simple, quick question to ask for little no time, right? So a graph question could be asked just to give you guys a chance to solve another harder problem with more time. That's how the instructors think, right? Do you have any questions are on the exam? So you have 25 questions, you have an hour to do them, right? 50 minutes, basically. So you have about 2 minutes per question, normally, right? However, some questions are give me questions, which shouldn't take too long, which should take less than a minute, right? Which you can use your time other places. That's how instructors think, correct? So long, hard ones should not be on there. There'll be a range between a couple hard ones to solve that take time, one that are just plug and chugs, and a lot of ones that are just kind of common sense. One of the common sense one could be a graph question. So, zero order reactions. Zero order in response to concentration over time. So what happens to reactants over time? They decrease, right? They go down. Which one of those is not going down? Okay, next up. A is zero order when looking at something else besides concentration. Do you guys know what? What? It's the rate constant. If it's rate constant over time, that's what it looks like, right? Not the actual concentration, the rate constant, or K over time. Now, if your graph looks like this, it's either it's going to be first order or second order, correct? That's rate. It's you solve for it. They both look like that. You learn in lab that we have to make it look like this by taking the inverse of it or the natural log of it. With concentration over time, the graphs will look like that because they're not equal. They get used up at different times. B is the right answer for this one because it goes steadily at the same pace. Kind of makes some sense? Okay. Nope. Because it told you it's what? Zero order. That's more important than anything else. The fact it tells you it's zero order. That makes sense. If it was first order, I would choose C. If it was second order, I would still choose C, even though that's technically a first order graph. A second order graph is a bit more steep, but it looks pretty much similar, right? They usually won't ask the difference between a first order and second order graph to you guys in response to concentration because they are very similar to each other to you guys. You don't have a lot of experience with the graphs yet. Don't quote me on that. Sometimes I do crazy things. I'm just letting you guys know what I would do if I made the test. Okay, number 10 is the first time we talk about half-life. What is half-life?
Would they ask us for the graphs for the rate constant?
They would ask you for rate constant. Yeah, it's a possibility. You can always ask for rate constant. Yes. So I would know the graphs for rate constant over time and concentration over time. So I would know. It would say rate constant on the axis. Yeah, on this axis right here. It would tell you at rate constant or concentration. You know, it's concentration because it has the brackets, right? It would show K. It was talking about rate constant. What's up? I can do one better. We have this magical resource called Google. So let's see, rate constant over time. Rate law graphs. Okay. So let's see if we get a bigger zoom up on this. Wow, that was helpful. That just made the picture smaller. That's great. Kind of what I'm looking at right here, right? This right here, if you notice, what you guys should be doing in lab class, so this might help you with lab, is this is zero order, this is first order, this is second order. You know that because what you're doing to it, right? You take the ln of something, gives you this first order. Take the one verse of it and it goes up. That should be second order. Okay. That's not helpful though. Let's see if we can find something else. I'm not comfortable drawing lots of graphs. There we go. First order, second order over concentration, but you're doing, again, you're manipulating it, which is not helpful. Ah, here we go. Please show up when I make it bigger, because I like this picture. Wait, maybe a little bit. Boom, there you go, Athena. We take a picture of it. I should you find it. Just go to Google.
That makes so much sense.
Okay. So, but there we go.
Do you think that one aspect is the difference between rate and concentration?
Yeah, knowing them.
Like, which one's a rate and concentration?
It could be, or they might just ask you which graph is rate, or exam, like which graph is zero order in response to grade over concentration or concentration over time. It would tell you, right? There you go. So that's how you would do it. Okay, is anyone else going to take pictures of this before? Yeah, what's up? Concentration should always go down, yes.
It just goes down in different curves.
Yes. In response to time, it will always go down, right? These things a bit differently because rate versus concentration, right? So does zero order have any role in on the rate at all? Yes or no? That's why it's a straight line. First order, it's a 1-to-1 ratio, right? So if I increase something by 2 and I get something out of 2, right? If I put 2 in, I get 2 out. Rise over run, basically.
So in the worksheets, it gives us weird slopes. Not slopes, but two different height slopes. So how do you know which one's rate and which one's concentration?
It should tell you. Does it not tell you what the axes are labeled?
It says type 1 the rate box. And concentration. But then we don't.
Bring it here. I'm in trouble. I just don't know. I don't have access to you guys' resources. You'd think they would give it to me, but they don't. Which ones?
Because on the graph that you showed us, that one goes down at a different curve.
Yeah,
but
but
then that one
look,
doesn't.
but let me see pencil. What's going on with the things?
Okay.
If you take the ln of this guy, right? It goes down. If you take the 1 over a of this guy, it goes up. You're still dealing with concentrations, right? The reason we gotta go over that is because you guys love y equals mx plus b, correct? You guys do not love calculus. So that's why in lab, hint, hint, in a couple weeks, your kinetics lab will be due, which is your formal lab report for my class. That's why you convert to y equals mx plus b. Much, much easier to calculate than the calculus-wise, the down graph arrow. What area reaches below that graph, right? You can thank Isaac Newton for that. That's all calculus is stuff below the graph. Okay. Any more questions on this one? If I'm fine answering questions. Okay. So back to number 10. What is half-life?
Time it takes for half of the product to go away.
Yep. Time it takes for half of the reactants to go away, not products. Right? So that, or we can do it with some type of radioactive material, right? But the half-life of something. So half-life is equal to what? Well, first order half-life is equal to 0.693 over K. So, we're talking about first order half-life right here, right? So if K goes up, right? What happens to half-life? Go down, right? If I increase my numerator, my denominator, if I increase my denominator, my big whole number goes down, right? Which should make sense. This is my rate constant, how fast my reactor is being used up to make products, correct? So if I have a huge K, right, my half-life should be pretty quick, right? So A is wrong. The half-life is inversely proportional to the rate constant. If K go up, what happens to T? Go down. If K go down, what happens to T? Go up. Are they inversely proportional to each other? Yeah, that looks good. However, hint, hint, wink, wink, when it comes to these questions, especially if you guys are in a grad school or you're pre-meds, you're taking the MCAT, do not just stop at the one you think is right. Keep going on. Because you could be wrong. So half-life is directly proportional. Original concentration of the reactant. Did I draw the original concentration of the reactant on here? Is that part of the unit? Did I draw concentration anywhere? These I'm involved at all. There's no concentration, doesn't matter, right? All I care about is K, T, and 0.693, which is a constant, right? A constant over a constant. So it really doesn't matter I could have the world's supply of this stuff. It wouldn't affect anything. Okay. Half-life is directly proportional to the final concentration. Again, there's no concentrations. And is not affected by temperature. Everything is affected by temperature. Now I know this. What is 0 Kelvin? What's absolute? What does that mean? Nothing moves. If nothing moves, can anything be broken down or made? No. So does temperature play a role with stuff? Yeah. So the only one we have is B. Does that make sense? Okay. No, we're not there yet. You guys aren't there yet. You guys are undergraduates, not graduate students yet. There is no most right. There would probably be an obvious one, but I want you guys to continue onwards. Okay. Yeah. It's a possibility. Is that when the equation's given to you? No, I'd memorize them. I know that Langley likes first order because it's easy to calculate. Then I guess you wouldn't test anything besides first order then. I know Langley makes more of the test, so I'm gonna go off what Langley likes. If Deo says something, he's also involved too. So just know first order then. So T 1/2 equals 0.693 over K. T 1/2 for half-life is equal to 0.693 over K. That's what you guys need to know. Okay. Okay. I know this was on the test, correct? Okay. Guess what? Most likely will be on your exam then too. Some of you guys got it wrong, some of you guys didn't. Let's talk about this. This guy's actually a pretty easy question to understand. So, if you guys had me for lab last semester, I did lie to you a little bit. I told you all reactions are it's a single step, right? It happens and we move onwards. That's kind of a lie. Things are always reacting more than one step. There's usually a fast step and a slow step, right? The slow step is going to form something called an intermediate, right? While the slow step is also recalled to as the intermediate step. And this is my attempt to spell. So if I get it wrong, I apologize. I am a science major, not an English major. So slow step equals the intermediate step. Okay. Next is I need to get that guy in here, right? So one of the ones I need has to have A and B in here. Does that make sense? And that most likely should be my slow step. Should have the rate constants in there. If that doesn't make sense to you, I need to make this equation, right? So let's figure that out. What side is this side right here? Reactants. You add reactants up, you add products up, get rid of common ones, right? Let's do it for A. So A plus B gives you F, right? And B plus F gives you 2C. Add them up. A plus F plus B is 2B, gives you 2C plus F. Is there any common occurrences here? If I get rid of F, is this the same thing as that? That's probably a good sign, right? But you want to look at all of them, right? So BB, that's good to have, right? That cancels everything out. So that would also give you this, right? The problem is in the second one right here, my slow step would be my rate law, my rate constant, right? Right? Constant is A and B inside of it, correct? Number B right here has what two letters? BB. That would be B squared would be my rate constant. Is that true? That's wrong. C is wrong for the same thing. It's AA. What's wrong with step D or number D right here? Nope, there's two B's. The fast and the slow step. So if you look real quick, I'm going to erase everything. G, it is made then used up. Right? It's a catalyst or an intermediate. It's actually not a catalyst because it gets destroyed. It gets used up. Catalysts do not get used up. It's an intermediate step. Make sure you know that. It gets made and then gets used up immediately right afterwards. That's what makes it an intermediate, right? It intermediates between the two of them, right? The reason is that your intermediate's always your slow step because you can only continue as long as you have that guy, correct? If I wanted to make a sandwich, I'd have to go kill a pig to get the bacon or ham, right? If every time I wanted a ham sandwich, I'd just go kill a pig, kill it, and get the ham, that would be my slow step, correct? Because I probably have supply of bread, correct? But I would need to go get the pig to get the bread, need the meat. That kind of makes some sense? That's going to take the time. So that's the intermediate step. Sometimes I refer to it as not the slow step, but intermediate step. They have to mean the same thing. Please note both of them. Questions like 11 will pop up on the exam. I can almost guarantee it because they popped up on your guys' quizzes. It was answered okay, but people had questions on it and some people got it wrong, which means they'll probably ask about it. Yeah, there's always two steps. Can you handle the responsibility? Okay.
No.
Cool. Okay. Now we're talking about catalysts. What do catalysts do? They speed up reactions. How? For which one, 11 or 12? No, 11 is wrong. 11 is B. Sorry, 11 is A, my bad. It's been a long day for me, guys. I had to repair my sink twice today because apparently garbage disposal didn't work the first time. That was fun. Cool. Okay, if the reaction has an activation energy of 125 kilojoules, again, Langley also makes it exams. Langley, for some reason, loves kilojoules. So anytime we have joules, just offhandedly convert to kilojoules. You're most likely saving yourself a step of work. It's just much easier doing that way. Okay? Okay. And as an energy of reaction or activation energy of 35 kilojoules. What would happen if I used the catalyst? So, yes, I'm going to post this recording on the YouTube channel again. I'll make it public for about a week, and then I'll make it private. Just make it easier for you guys to get to it. Okay. So a catalyst or enzyme will decrease activation energy. What does that mean? I'm going to decrease activation energy or energy of reaction, basically, right? So I'm going to make one of these numbers go down and one of the numbers stay the same. Which one goes down? The 125, that's my activation energy. Catalyst, lower activation energy. So out of A, B, C, D, and E, which one is lowered? Good. What's the between C and E? What does energy of reaction mean? That tells me if I'm exothermic or endothermic. Catalysts do not mess that up, right? If something is exothermic, it will always be exothermic, right? It's not, I'm not using a catalyst, just makes it happen faster. It doesn't change how much energy is released by it or taken up by it, right? That never changes. So the answer for 12 is E. Does that make sense? Okay. Cool. Okay. If the rate constant of reaction order is increased by a factor of 2.5 and the temperature is increased from 2 to 2, what all does this mean? Well, I mentioned this thing down here, activation energy, right? I have two ranges of temperatures, correct? I mentioned rate constant. So what does this mean? I'm probably have to go back up to your problem, your question, your things given to you and figure out which one has everything. Hint, hint, wink, wink. It's this one. Please use the 8.314 when dealing with activation energy. Do not use the gas constant for that one. Use this one. Okay. So we're going to take this guy and we're going to move it down here. Okay, so natural log of K1 over, sorry, K2 over K1 is equal to activation energy over R, T1, T2. So let's plug our things in. If the rate constant of reaction increased by a factor of 2.5, what does that mean? Something increased by a factor of 2.5, correct? So I think 2.5 would be my K2 value, right? Because K1 can be any number I want it to be as long as K2 is 2.5 greater than that by a factor 2.5, right? So let's make the math easier on us. Make K1 1. Make K2 2.5. It's just easier to do that, right? Because that's 1 to 2.5 is an increased factor of 2.5, correct? That's much easier than making K1 2. Next up, activation energy. That's what I'm solving for. I'm going to plug in X value in for there. R, 8.314. Great. I have two temperatures. Problem is what? They're in Celsius. Is that good or bad? Kelvin. How do I go from Celsius to Kelvin? Yep, 273. So 22 plus 273 is what? $35 plus 273. The reason why it's T1 minus T2 is because they're inverse of each other, right? So T1's technically going to be greater. So, what's 1 over 295 minus 1 over 308? (1.4) times 10 to the negative fourth. Okay, that is that guy right there. Let's use a different color. Oh God, that's so many comments. What's going on? Is the given constant? Yes, it's given. Huh? We're going to convert to kilojoules. Yes. Whoops. Okay. Boom, boom. X 8.314 is equal to 2.5 over 1 ln. So the next one I would solve for probably is this side right here. So what's the ln of 2.5? That's correct. 0.916. 1.4 times 10 to the negative fourth. So, solve for x first. What would I do? I have 2 more variables to get rid of. 8.314 and 1.4 times 10 to the negative second, the negative fourth. Right? Which one you get rid of first?
Dude, see, I'm on now,
1.4?
but only through the
Oh,
phone.
someone's talking. What's up? Cool. Divide by 1.4 times 10 to the negative fourth. Can make me a really big number. 6404.17. Then I'm going to multiply that number by 8.314 to solve for x. Okay, that's right now. I got something akin to what? 5, 3, 2, 4, 4, right? That's in joules. Is that what I want? I want kilojoules. Divide by 1,000. Yep. Yes, you not get that? What'd you get? So I divide. So this is what I did. 0.916 divided by 1.4 times 10 to the negative fourth. That's what I did to get that guy. Did you not get that? No? I could have typed something wrong. What did you guys get instead? $6.5? $9.61 divided by 1.4 times 10 to the negative fourth. Try using parentheses, see if that helps you. Yep, Madison, Savannah, let person in. Thank you. Okay, so you got it, what I got? Okay. When you guys are using these, when you guys are doing it times 10 to the fourth power, make sure you're using parentheses for everything and do everything step by step by step. Okay. Let's get going because unfortunately I have to do a project when I get home for school. Woohoo. Okay. So doing that, divided by 1,000, I got 53.8 24 something. It really doesn't matter as long as I get the 53. Now, which one of those is close to which one I got? Move that over by 1, 5.3. Does that make sense what I did? Most likely one of these things could be asked on your test. Okay. Anyone have any questions on this one?
Hey Shane,
What's up?
I have a question. So it wants it in kilojoules per mole though, so would it be A actually?
No,
I thought we had changed to joules for some reason.
we did. We went from
Oh.
joules to kilojoules. I already did it before.
Oh, okay. Never mind.
Probably. There you go. That number divided by 1,000 will give you 53. So.
If you put the decimal from there, then it can be different.
Yep. There'll be answers that are close, that are wrong, but you'll do it if you get messed up. So make sure you guys do your problems correctly. Cool. 14. If the rate or first order rate constant, boom, how long is for 3/4 the initial concentration be used up? This basically means I'm just going to use the first order reaction again, which is ln of A final is equal to negative KT plus ln of A naught. And I know that because it tells me it's first order, gives me a rate constant, it mentions initial concentration, right? Okay. So initially, how much stuff do I have? About 100%, correct? When I first start off, 100% of something, correct? What? So how do I do? How do I say something's 100%? I just call it 1, right? And then how long is required for 3/4 of the initial concentration to be used up? So how much stuff is left? 2.25 or 1/4, right? Convert that to 0.25. That makes sense what I did. I like ones like question 14 because you know why? What's ln of 1? I just saved you a bunch of time. So ln, oops, ln of 0.25 is what? Cool, thank you. Cool, yep, and that is equal to negative K, which is 5.48 times 10 negative second. And then what I'm looking for time. So how do I solve for time? How do I solve for t? Divide everything by 5.48 times 10 to the negative squared. Correct? Kind of make some sense? You good? Am I going to? Yeah. So I took the ln of 2.5, right? And I know that because how long is 3/4 required of my initial concentration to be used up, right? Well, I'm using basically percentages there, right? 3/4 is almost 75%, correct? So I had to start off with 100% of something. That's why I put 1 in for there. Okay. There we go. So what do you guys get? Negative 1.386, negative 1.386 divided by 5.48, negative 2. What do you guys get? 25.3. Does that make sense? No? You're off by a lot. Did you make sure you put parentheses here? Did you? Got it? Okay. ln, so do me a favor, type in ln of 1 in the calculator for me. That's why I canceled out. ln of 1 is just 0, right? So anytime you have to deal with 100% of something, or you're dealing with a percentage of something at the very end, you can usually just cancel out ln of initial concentration because it's just 100%, right? That's why questions like 14 are easy. I would consider this a one-step problem because you just plug it in, divide by one number, you get it. It shouldn't take you guys too long to do, right? So they might ask the question too like this. Okay,
Shane, I have a question.
I have an answer.
For, you know how with the 3/4 part,
Yeah?
how would we, you know how the wording affects like whether you plug in 0.75 or 0.25?
Yep. So how long is 3/4 of the initial concentration to be used up? Right? If something is used up, what's that mean?
That it's already being used up?
They're being used up, right? So what is left over?
Okay, so we're just, that's the leftover parts.
Yep.
Thank you.
3/4? How long would it take for 3/4 to be remaining? How long would it take for 1/4 to be used up? Stuff like that. So the wording of it is very particular, which does suck, I understand. So if you guys read it very carefully, highlight it, underline it in your head if you need to, write it down, but that's what they would say. That kind of makes sense? Okay. Cool. So, interpreting graphs. This will be on my final for my lab class. So it's always good to go over this now because I like graphs. So at what point in time would H2 be the highest?
At initial?
Initial. Is that one of the answers I can give you though? No. So what's the second best one? A. Does that make sense? At what time would it be the lowest? The final, or B, right? Good. That's what this graph is just saying. Correct? What order is this? Probably first or second order, right? You wouldn't know because it's hard to tell. You'd have to do the inverse of it to figure it out. That's why, hint, hint, in the kinetics lab, you have to have 3 graphs in your final paper. One to the one with natural log and one to the inverse to figure out which order it is. Okay. First order, for a first order reaction, initial reaction, concentration, 25 days later. Then something is a half-life. Then it's half-life. What? What's going on here? So this right here, I would consider number 16 a 2-step problem. The reason I call it a 2-step problem, we use 2 different equations to solve for it. The first one is negative KT. The reason we're doing this is because, make this negative real quick, sorry about that. Negative KT. Because I don't have the K value, correct? And what do you need for half-life for first order? So I can't solve for half-life until I have this guy, right? So I got to solve for the first equation to solve for the second equation. This is why I call it a 2-step problem, because you do 2 different types of equations, right? These ones take longer. There's going to be less ones like this in your test because you don't have as much time. Does that make sense? Okay. So initial concentration gets plugged into here. Final concentration gets plugged into here. Time gets plugged into T. Solve for K. So You guys want to continue going over this one? Or you guys want to figure this out yourself after telling you how to do it? What do you guys want? Anyone want me to go over this one? Cool. So, number 17 is kind of weird. I do want to go over it. It is kind of weird. So, whoops, it is easy. So, please let the person in. Thank you. Half-life, right? T1/2 is equal to 0.693 over K. Cool. So, what value am I missing? Okay. It's right there, 0.666, which is funny because we go to a Christian college, I think at least.
You don't have to change it from minutes.
Nope. Well, I would change it in minutes to seconds. Yeah, I would. So multiply by 60.
Did they just throw you the 160 degrees Celsius and 3 off?
Yep. Because remember, half-life is temperature. Temperature is necessary, right? But it's not. It is necessary because if it does affect it, right? But it's not required for the formula, right? The half-life is only works at this given temperature. If it's 661, it would be a different half-life, theoretically speaking. Correct? Okay. So 660 times 60 gives you what? 39.96.
I'm sorry, why did you multiply it by 60?
Because I need the answers in seconds.
Oh, okay. Right, thank you.
Let's do it afterwards because it make more sense. My brain. Sorry, I messed up somewhere. Same thing. K value, let them in, please. Whoops. 0.693 over K. We'll make it just the same. We'll just, whoops, 660. 6.660. 0.666. Right? Solve for it normally, then we'll convert afterwards. So it's equal to 1.04 minutes times 60. Does that make sense what I did?
So just don't convert it into off.
Yeah, for this one, don't convert until after. I would just on a roll, don't convert until after solving for everything. Okay. Yeah, you're almost halfway done. It only took us about 2 hours. Woohoo! So we're gonna go a little higher, a little further. Because you guys, I still want to go over the other one because some of you guys did better overall on chapters 15 and 16, but okay. So over here, I'll have energy. Why do I have a pen? Here I'll have time, right? Here's a typical energy state. It's a typical energy diagram, right? So over here, I got my reactants. Over here, I got my products. At what point in this graph did reactants become products? At the top, right? Because that's the activation energy. I have to get over that hump to convert it, correct? It's found at the highest energy points. Does that make sense? That's what the transition state is. Okay. We're going to skip 19, go to 20 because I like 20. Okay. Just 20, I can guarantee will be on the test because it's kind of weird like this, right? So, A is to what A is to what power? The rate law of the reaction involves only A and B. First order in A, so what number should I put right by A? And B is what? And the fourth order in B, respectively. If the concentration of A is increased by a factor of 4, so what do I plug into A? So 4 to the first power. And the concentration of B is tripled. Right? What will the new rate be? So what's 4 to the first power? What's 4 to the third power? What? 3 to the fourth power. Okay. What's 4 times 81? Which one do you think it is? Does that make sense? Again, here's one of those one-step problems, pretty quick and easy. That's why I can probably guarantee one like this will be on there if there is any math ones like that on here. Okay. Ugh. Okay. I'm going to skip 21. I already went over in a previous video, but you guys know how to do stuff like this and find the rate. Again, one like this will be on there. Either like this one or the other one, or I think number 6. Okay. Same thing with this one. I won't go over 23 and 22. It's the exact same thing. Question 25 is literally question 6. Okay. So 26. Given the mechanism, which one is the rate limiting step? Also known as the slow step, 1 or 2. Why? No, it could be. It could be, but that's not a good way of doing it. Because not the catalyst, intermediate. You gotta be very careful with your wording, especially when talking with Langley. It's because he's a physical chemist. Words are very important to physical chemists because they write papers, and wording is very particular. It's very annoying, I know. But there's your intermediate. I also know because K is that. There it's found. Does that make sense? There's 2 ways of knowing which one's the rate limiting step or the slow step. Step 1. Does that make sense? Question like that will probably be on there.
Wait, I'm sorry. Why is it the rate limiting step?
The rate limiting step is referred to as a slow step, right?
Yeah.
The slow step always forms an intermediate, which is not found in the overall reaction. Right? So this, number 1 is forming that. But I also know my rate law is found from my slow step because that's the most important step, which is this guy right here. That kind of makes sense?
Yeah.
That's how you know.
Okay, thank you.
Of course. Okay. Okay. Activation energy. We kind of went over one just like this. Do you guys want to go over another activation energy one? Yes or no? Or does it plug and chug?
Yes.
Yes? Someone said yes. Cool. Here's the equation here's the equation I'm gonna use. It should be given to you. Yeah, 27. So, whoops, easy. ln of K2 over K1, parentheses, is equal to EA over R, 1T1 minus 1T2. So plug and chug. So I have temperatures, but can I use these temperatures in this position right now? Yes or no? No. Add 273 to both of them. Make them Kelvin. I have K1 and K2. Put those over each other. I'll do so in red. Please let the person in. Thank you. If one of the co-hosts could just take a picture of all the people in attendance in the Zoom call, I'd I'd like that, please, so I can record that I'm helping students. Okay. I'm looking for EA again, so I'll leave that blank. This would be 8.314. 30 plus 273 is 303. 1 over 303 minus 49 plus 273 is 1 over 322. Okay. Solve for both sides. So 1.21 times 10 to the negative third, 1.38 times 10 to the negative fourth. That guy divided by the smaller guy. Take the ln of that guy. Oh, that's not what I want. Change colors. Let's do hot pink. 2.17 is equal to EA over 8.314. 1 over 303. 1 over 322. That minus that. This making sense so far? Well, maybe the person didn't want to go over it. That's what I'm talking to.
Yes.
Okay. I want to call you out. Let's make sure. You don't have to say anything. But I just want to make sure it's making sense to you.
Thank you.
Of course. That's what I'm here for. So divide this entire thing by 1.95 times 10 to the negative fourth. Changing colors once again. Let's go army green. 1, 1, 1, 4, 3. I'm not going to write any decimal places because it's already getting gigantic numbers. The decimal places become less important. Take that divided by 8.314. That will give me 92643 joules. Divide that number by 1,000. And I get 92.64, which is close to 92.7. Okay. Does that make sense? Cool.
Thank you.
Of course. Okay. Which the following is first order. The following is first order. Solution is this to this. 45 minutes. The half-life is this. Again, 20 is another two-step problem. We're going to solve for. That's what you do. Figure out K. Right? Then using half-life, plug K in. Does that make sense? Do you guys want to do this problem? You want to skip it? Okay. And I have an entire video on this exact PQ.
Is the half-life ln 2 over K?
Yes. Yeah. Pretty much what it is, but I just remember it's 0.695. Makes my brain, makes it work some easier in my brain. Okay, talk about this graph. So, energy graph again. Woohoo! 29. What letter shows activation energy? No. Activation energy is the hump. So from this all the way to the hump, A is activation energy. That's the energy this guy has to overcome. Does that make sense? That's why that's A. I don't know if this will be on your test or not, but it could be. Then it will probably be on the test. So that's A. Which letter shows the change in overall energy? What do you guys think? Which one tells the difference between the input and output? D. D tells you the change in energy, right? If it's exothermic or endothermic. I started here. I ended up here. Did I gain energy or lose energy? So most likely, I'm going to be endothermic. Sure, I'll make everything public and drop the playlist, Matthew. Shoot me an email and I'll shoot you a link to all of them. Again, if there is a link that I did not post, do not click it. No, a student clicked on it and told me. Yeah, that was awkward because right after I posted my Kahoot and like, oh, cool, and it's like that was fun. So no.
What was it?
So I'm gonna stop sharing for a second. Okay, back to recording. Cool. Hopefully I didn't mess up the recording, the audio. We'll find out. So that's fun. Okay, which one shows a use of a catalyst? E shows a use of a catalyst, right? Because it's lowering activation energy. So here's normal. Here's a catalyst. Does that make sense? Okay. Cool, cool. So catalyst lowers the activation energy. How does it do it? Does it increase energy at all? Does it change concentration? Does it affect exothermic or endothermic heat? Does it add heat? Does the catalyst do something at all? It does something, right? It adds an alternative pathway. It goes back to 181, guys, right? You have this weird looking blob, and then you have a nicer looking blob. It's a catalyst. They both do the same thing. It's just another pathway. It's a bit quicker. That's all a catalyst does. Okay. Colligator properties. What is colligator properties? Come on, guys. Why? So what is colligator properties? Good. But what is it? You guys are memorizing it, but what does it mean? This is great to memorize things. You guys understand the things. Colligator properties, what binds molecules together, right? So if I increase the bonding force, I increase boiling point, right? It takes more energy to break the molecules apart, correct? If the molecule's at a colder temperature or frozen, that makes them closer to tighter, nice and tighter, right? Takes more energy, right? It takes more time to melt snow than it does water, correct? So I have to change it to different forms of matter. The only thing that doesn't matter is the density. That doesn't affect bonding force at all. That's just something's mass on gravity, right? Cool. What's up? Okay. I don't know if I said anything weird. Oh, okay. When a non-volatile solvent or solutes is added to a volatile solvent, Vapor pressure does what? Freezing point does what? So what does this mean? Okay, so when I have a solute, I like to draw a cup. Okay, so what does a volatile thing mean? Gasoline is very volatile. You go to a gas station stop. Huh? No. It turns into gases very quickly, right? That's what I'm talking gasoline. You all know what gasoline smells like. If I take gasoline and just dump in this room, as soon as the gasoline hits the table or the floor, you can instantly smell it, right? The liquid particles like to go to a gas particle very quickly, right? Which could be violent if I light a match in here, right? But that's what it means. It goes to a gas very quickly. So I have some type of liquid, right, that wants to be a gas. And then I just take a bunch of this solute or rock stuff and throw it on top. And that doesn't want to turn to a gas. It wants to stay a solid. How does it affect stuff? What do you guys think? How does it affect the vapor pressure? So vapor pressure actually is going to decrease. The reason being, the rock stuff's in there, right? Let's get a bit bigger. So think about this. Where we're thinking about it. If I take a cup of gasoline and throw some salt in it, right? Gasoline is a solvent, correct? It will dissolve things in it, correct? It's not a good solvent, but it will dissolve things. So if I throw salt into it, the gasoline's going to worry about the salt first before it turns into a gas, right? It needs to worry about the stuff I added to it, right? Dissolve that stuff first and then turn to a gas, right? So overall, it's actually going to decrease vapor pressure because it's not worried about turning to a gas right now. It's worried about dissolving the stuff first, right? It's going to increase boiling point because adding a solute to a solvent actually does increase boiling point. If you don't believe me, take a pot of water, add some salt to it, it actually will boil quicker. It's an old Italian trick. Or at least my grandma told me. My grandma's never wrong, because if she is, I get slapped. It's going to decrease freezing point. Does seawater freeze? No, but seawater is pretty cold, right? Adding salt to water makes the freezing point go down. And vice versa. The freezing point goes down, boiling point has to go up. They're kind of the opposite of each other. Osmotic pressure will also go up, right? That should make sense because I added a salt to a liquid, right? I'm changing the osmotic pressure of it, correct? Okay. That's how you would solve this problem. That kind of makes some sense? 35. So the process known as osmosis, which is the movement of water from what to what? High concentration of solvent to a low concentration of solvent, right? You guys should have pictured this U-shaped contraption, semi-permeable membrane, right? Water equal on both sides. If I dump a little bit of rocks into here, a little bit of salt into here, and a ton of salt into here, right? Water is going to move from low concentration to high concentration. So our water is going to move towards stuff. So from low to high, right? So what moves through it? That's the solvent or the water, right? So solvent, solvent, solvent. And it's going to go to the higher solvent. It's weird to think about it, but the water on this side is going to go to this side, make the water go up. That's why it's E. Question 35 is worded really weirdly, but it does make sense if you think about it. Why? That's not how that works. No, you want to go from lower solvent to a solvent. No, I don't like that. Okay, let him in. Okay, 35 is a bad question. Cool.
Oh my god.
So, you guys know your intermolecular forces at all?
Yes.
Which one's your strongest one?
Hydrogen bond, ion dipole. Ion dipole. I'm not muted.
You're not muted. No, you're not. It's ion dipole. What does that mean? Thank you. You're enthusiastic. I need that energy right now. Okay. Ion dipole is the same thing as saying ionic. What type of bonds do ionic bonds form? Come on, 113 people. Metals and a non-metal, right? So I take the metal, so any of the things from group 1 all the way up into like the staircase, right? All those are metals. Anything right of the staircases are all the gases, right? So if I take a metal and a non-metal, or a metal and a gas, boom, I form an ionic salt. Good example of ionic salts, sodium chloride. You try pulling those things apart. It's very hard to do so, right? So that's my strongest one. So if I'm going from weakest to strongest, what should it be? Ionic on the end. Get rid of A, get rid of C, get rid of D. Okay, what's the second strongest? Hydrogen. Ionic, hydrogen, then dipole, dipole, then London dispersion. London dispersion, it takes place where? In everything. It's why molecules don't interact with each other. It's the pulses of the electrons pushing away from each other, right? Everything is London dispersion forces. We only care about London dispersion, though, when dealing with non-polar molecules. What are some examples of non-polar? Have no fear of ice cold fear. The diatomics. So if you have one of these diatomics or a molecule that's just carbon and hydrogen, these guys right here are your non-polar molecules. If it's any other gases combined with each other, it's going to be dipole-dipole. What makes something hydrogen bonds? What's hydrogen bonding? When does that occur? When hydrogen's bonded to what molecules? Nitrogen, oxygen, and fluorine. Hey, if you guys look at the periodic table of elements, those are the most electronegative compounds there. That makes sense? They're so electronegative, they basically make hydrogen act almost like a metal. Hint, hint, wink, wink. That's why it's in group 1. Okay. There you go. That's IMFs right there, intermolecular forces. So,
Hey, Shane.
what is vapor pressure? What's vapor? Gas. So, if I were to take...
Shane, Mike had a question.
Oh, sorry.
Hey, what did you say the answer was for 35?
35? The answer technically, I think it's E. Deo says it's B. I don't like the way it's worded. Go take it up to him. Because technically,
Yeah, 'cause
it's
it's
going to
the-
be solvent
yeah, it's the
moving to a
inverse of it.
solute, but it's none of them up there. That's like that.
Yeah, I just wanted to make sure because
The key
yeah,
says
because
it's
it's
B.
like the inverse of it. So it'd be higher solute or lower solvent.
Yeah, I don't like it. It's worded bad on purpose to trick you guys.
Yeah, I just wanted to make sure. Thank you.
Of course. Okay. Vapor pressure. So this is not recommended, but if I take a closed container and I put a very volatile liquid inside of it, right? And the liquid kind of wants to be a gas, right? Because it's volatile. Pressure builds up in that thing. If I have too much pressure, what do I just make? I go boom. Whoa. I don't recommend doing this, but hey. So vapor pressure is the pressure That's right there. When something goes from a liquid to a gas, right, it's making gas pressures right there, and it's going to react to something, right? Usually this occurs in a closed container. Why? Because there's outlets, tailpipe, right? The engine block, the hood of the car, there's outlets to places. It's not completely sealed up. But if I take a completely sealed up thing and put something in there and I kind of shake it, right? I put a match in there, it will blow up. That's why. Okay. Kind of like soda bottles, yeah. Okay. So you have higher vapor pressure when the liquid turns to a gas, right? So hint, hint, wink, wink. The lower the boiling point, right? So things that boil quicker have a higher vapor pressure because they're going to be gas. Now, you have any foreign people in this room? What's room temperature in Celsius? 25 what? 25? What do you say? 25 degrees Celsius, right? Cool. So, which one of these guys is going to be gas at this point? None of them, right? Which one's closest to being gas, though? Diethyl ether. If I take diethyl ether and spray it in front of you guys, it actually will evaporate in front of you. Welcome to organic chemistry. You can throw this stuff on someone and it will evaporate before it hits them in Arizona. That has the highest vapor pressure because it has the lowest boiling point. Does that kind of make sense? Cool. Okay. Okay. 38. So, the binding force in molecular solids. What the hell is a molecular solid? You actually do know what a molecular solid is. So what's molecular mean? Molecules. So let's, I don't know, take liquid oxygen. I don't like liquid oxygen. Solid oxygen, right? I don't know what this fun fact is. Cool. Yeah, it can be. Anything can convert to a solid at low enough temperature, right? That's what a molecular solid is. I took a molecule and I froze it. That's what it is. Yeah. But that's basically what a molecular solid is. Easy way of memorizing it. I took a thing and froze it. So, London dispersion forces are going to be present, correct? Most likely there. Good. That one makes sense, because if I take oxygen and I freeze it, that's molecular solid. Molecular solids are usually nonpolar molecules frozen. Ionic solids have a high melting point. Is that true? If I go take a Himalayan, if I take like a giant chunk of salt rock and I go try to burn it, will it take a while to turn it into a liquid? Yes or no? No? You go cook up salt rock for me. It takes a while. It's a huge chunk of matter. It takes a while. You guys did this in Chem 113. You boiled water, right? From ice onwards. If you didn't, be lucky. You will do it eventually in some of your labs. Doesn't work. Insulators. My engineering students, what's an insulator? My electrical engineers should know what this is. Not yet? Okay. Insulators stop electricity from going through. Okay. If I take a giant piece of salt rock and I took a conductor on one side, will electrons go through and shock on the other side? No. Right? No. Right? So they are insulators. Good. Molecular solids have a high melting point. Yeah, that one's wrong. D is the correct answer. Look for the incorrect statement. Molecular solids have a low melting point because they want to be gases, right? They are solids because I froze them at a very, very low temperature. Does that make sense? Okay. Okay. 39. I can guarantee one of these will be on here because this stuff right here confuses you guys. So, alligator mouth. It eats the biggest one, right? There we go. And then weird looking monster creature. Yep, and it's got wings. Cool, and hands and feet. Great. I don't know what it is, but basically I'm trying to show you the alligator mouth eats the biggest one, right? Okay, so which one of these guys would be a gas first? Probably neon, because that's a noble gas. It's in its name. So neon should be first. Okay, what's next? Well, it kind of tells you what's next. C2H6. The reason for this being is because what's this OH bond right here? What type of bond is that? Hydrogen bond. Hydrogen bonds makes the boiling point go up, right? You can think about this because I'm going to get in trouble for saying this, but hydrogen bonding is what makes alcohol, ethanol, right? You guys ever tried boiling alcohol? It's kind of hard to do. I can talk about this because my uncle's a moonshiner, or was a moonshiner. That's how one of my family made its money and then lost it all because they're crazy people. It would be near the end, right? Boom. Lastly, this guy is the strongest because potassium. Is potassium a metal or a non-metal? It's a metal. Boom. Okay. What type of intermolecular forces is found with HBr?
Shane, I have a question.
I have an answer.
That means KNO3, that's the highest boiling point, right?
Yes. Because it is ionic. Ionics will always have the highest because it's you try cooking something, you try cooking salt. It's not easy. That fell off. That's fine. I'll get in trouble for that later. Cool. So HBr, hydrogen bonding, right? The IMF between helium molecules. So helium, noble gas, right? Polar, non-polar. What do you guys think? Is it bonded to anything? No. It's going to be non-polar, which means all you have is that guy. Now, 42 is tricky.
Shane,
Yeah?
40 is dipole-dipole.
40 is dipole-dipole? Oh, my bad. Yep, because hydrogen bonds on with nitrogen, oxygen, and fluorine. My bad. Sorry, guys. I missed that one. Thank you for catching me, Madison. Yes, 41 still under dispersion, yes. Okay. 42. So what's going to hold the individual atoms together? So what holds these guys together? What's that bond? No. The individual. It's polar covalent. Because it's the individual atoms, right? This is an atomic level, right? This is not between other molecules. If I had other molecules of this guy, right? And they interact with each other, that would be hydrogen bonding if they're interacting. The individual atoms, though, is covalent, or polar covalent or non-polar covalent. That's what I'm trying to get at. So you're talking about the actual atoms, polar covalent. Does that make sense? Okay. 43 is asking about a sample of that together. That would be hydrogen bonding. Because it's a sample, a bunch of those stuff interact with each other, not the individual atoms interact with each other. Okay. Okay, the rest of this I'm gonna kind of skip because we need to go to this chapter. Yay, we're halfway done. Woohoo. Yeah, I know. I went a little slower on the last one because it's been a while since you guys have seen that one. If you guys want to go now, go ahead, go. I'm fine with that. If you haven't signed my sheet before you go, make sure you sign my sheet up there. I'm just taking attendance, make sure who's showing up and who's not. Can I post the first half? I'll post the entire video. I already have 2 other videos with this up, but yes, I will. Yes, I will. Okay. So, what is equilibrium? I will make sure I'll make it public in my video when I get home tonight. Yep, of course. Okay.
Professor Dunn,
What's up?
I love you.
Okay.
Yeah.
Okay, thank you. You guys can say that to me, but I can't say it to you because that's a Title IX violation if I say it to that, if I say it to you guys. So it's kind of weird. I can't reply it. It is. It's weird. It is odd. Welcome to my job. I spend an entire week going over stuff like that. Okay. So equilibrium, it's when the products and reactants equal each other. The way of saying that is when the forward and reverses are equal to each other. So the way of saying that is when Kf for forward equals Kr for reverse. That arrow is technically going forward. This arrow is going backwards. That makes sense? So Kf, Kr. What Kc is the concentration? Oh, the answer is C. Why is the answer C? Where's going forward and reverse? The rate of the constant, rate constants of the forward and reverse. The rates of the forward and no constants. That's what I want. When Kc equal each other, right? Is it C in your guys's?
I'm sorry, Shane, but yeah, it's C.
Whoops, my bad, because that's constants. I messed up. The answer is C then. Okay, that's my bad. So the answer is C. It's not A because the constants. My bad. Okay. That's why it's C, not A. Cool. Okay, number 2 is what? Which of the following will change the value of equilibrium constant? So, K is products of reactants, right? At any given temperature, if left alone long enough, the value will equal what K equals, right? K is always going to be true if given enough time. The only thing that can change K is C, is temperature. Does that make sense? Yes? Okay. Number 3. So, oh God, what's going on in the chat? Okay. K is equal to the concentration of products over the concentration of reactants. Right? So, good. That's going on there. The issue is that guy right there. So what's going on here? It's flipped. What's that mean? So normally this K right here is equal to 794, right? But then I flipped it, so that means I take the inverse of it. Correct? Does that make sense? What else did I do? Take the square root of it because I divided everything by 2. So 1 over that is what? Does that make sense what I did? You flip
Can
the
you do that
arrow.
again?
Okay, yes. Okay. So the equilibrium constant for this guy right here is 794. This to this, right? Well, what I did is I flipped the arrow, right? Because now this guy, which was a product, is now a reactant, right? So now I'm going backwards. Now, what's saying go backwards is taking the inverse. Now it's 1 over 794. But that's also not it. I'm also making half the amount, or dividing by 2, which is the same thing as taking the square root with k. So 1 over the square root of 794 will give you the answer, which is A.
Okay, I also have another question.
Okay.
So on quiz 2, we had one like this. This was that it was about Kp though. It was like the equation of Kp, and
Okay.
it had the coefficients as 2. What would
Okay.
you?
The coefficients were 2. Did it increase by a factor of 2?
I believe so. Yeah.
Then you're going to square it. If it increases by a factor of 2, that corresponds to squaring something.
Okay, and you don't do like 1 over it.
Well, did it reverse the order of it? It did?
Yeah.
If it did reverse the order, then it's 1 over the square root of the thing.
Okay.
I don't have the problem in front of me, so I don't know what it looked like. But the paper is saying yes, it was the inverse of it. So yes. Okay. That makes sense? This is the correct answer. This is the hypothetical question I just answered. Okay. Any more questions? Cool. People are losing it already. Woohoo! Okay. So K is equal to products over reactants. First off, what 2 things do I not care about? Anti-solids, anti-liquids. Don't care, don't care. So, next up, Kp is what? Constant pressure. If I'm talking about Kp, I use parentheses. P for parentheses. Wink, wink, hint, hint. Because brackets mean concentration, which also equals moles, or call me molarity. So you're going to have CO2 times H2O. That number right there means it's squared over CH4. The P's just mean pressure as well. So which one kind of looks like this guy? A. Does that make sense what I did? Okay. Moving on, number 5. One of the very few math ones with this. Okay. Oh, give me a second. Like talking like Porky Pig right now. Oof. Okay. NO, oop, oop, N squared plus O2. Good. A closed vessel is injected with. Cool. So what this means is since I'm doing something to it, I need to form an ice table. Which ice tables are great. All right, because I'm looking for the partial pressure of O. So what's the I stand for in ice? So initially, how much reactants do I have? Good, I injected 36 ATMs, right? 115, yes, it's always zeros. Because initially you don't have any reactants yet, right? You then are subtracting by x, add x, add x, right? The issue with this is, oh God, this is the one I've used the freaking quadratic formula for, isn't it? I don't like the quadratic formula.
We didn't use it last time.
We didn't.
We just used that.
Yeah, I know. Okay, that's height of this ice table, right? Here's your KP value. So, changing colors, 2.4 times 10 to the third. I'm going to erase all of this stuff. Select all of that, and we're going to delete it. Go back to my drawing. Is equal to x squared over 360.1 minus 2x. So, right? I messed up somewhere, 1 second. No, you can't do that here because you could do that. That's theoretically you could do. If the x is negligible, we can assume it's that. The issue is though we can't because x is not negligible.
How do you know when it is?
Is it more than 10%? It's more than 10%, trust me. We only can ignore it when dealing with acid and bases because the concentration of hydrogen is usually in a 10 to the negative something, which is a very small number, right? This is not going to be a small number. It's going to be a big number. I'm going to skip this one now because I don't want to go over everything. I went over my last video. That should be up. So we'll cover it there. Go watch that one. Sorry, I just don't want to spend too much time. I do have homework of my own I have to do. Sorry about that. But this one I think is more important anyway. This cube problem right here. So, K is equal to what, guys? I keep mentioning this because I just want you guys to do this. What's Q equal to? Products over reactants. Q is the experimental quotient, or what I'm experimentally trying to get, right? If I change the concentrations of my products or reactants, right, that theoretically would change my K value. Well, we're good there, right? But I just told you the only thing that can change K is temperature, right? So if I change the products and reactants concentrations, I can't theoretically change K, right? So K becomes Q. So Q is just K until it can get to K, right? So if K is equal to Q, it's at equilibrium. If Q is bigger than K, right, what happens? Well, I need to make Q equal K. So how do I make Q bigger? Sorry, how do I make Q smaller? What do I do? I'm going to add more reactants. Adding more reactants will make Q go down. Does that make sense? So I'm going to shift to the right to make more reactants. If K is less than Q, I shift towards the left, make more products. Does that make sense? So how is the reaction quotient used to determine wherever that is at equilibrium? Right? The reaction is at equilibrium? No. The reaction is at equilibrium? No. No. The reaction quotient must be satisfied for no. E. When they equal each other, then they are at equilibrium. Does that make sense? And that's what Q is. Yes. So no, so K is the rate constant, right? It's always constant for that equation at a given temperature, right? So for example, A plus B will give me C, right? And the K for that value, let's just say it's like 4. If I triple that and quadruple that, right? Eventually over time, I'll get this value, right? But at a certain, if the temperatures remain constant, right? However, I'll get a Q value instead, right? Because it'll be different at first. I can use the hypothetical difference between these two to figure out what the relationship will be. That's what Q just is. It's the experimental quotient, right? So if I change the concentrations up, right, I get Q instead of K. Yes, K will be at a given time, at a given temperature, right? You have to make sure they equal each other, because they will eventually. How do you make them equal each other? Is what you're trying to get at. Okay. You mean a doctor scale? You mean an equilibrium scale, or just a scale scale?
You know when you go to the doctors and you step on that scale and it like shifts like that. So you put it
It's just called a scale.
No, it's a doctor scale. I don't know what it is.
No, you don't have a
You mean
scale at
manual
home?
scale?
You don't have a scale at home? You don't have a weight scale? That's good. Don't get these. These are bad for you. But like the weigh your food out? You don't have one of these at your home? Yeah, because I live with my roommates they're on a diet, so they have to weigh their food out. And I have to participate because I'm a good roommate and it's awful. So I eat behind their back all the time. I can't, no. I know what doctor scale you're talking about. It's just, yeah, sure. I mean, if you want to, you can think of anything like that. If it helps you, do whatever it helps you. Okay. Yes, you're correct with the analogy. Okay. In the coal gasification process, carbon monoxide is converted to carbon dioxide via the following reaction. So, what concerns me about this problem is the last parts. At equilibrium, there will be remaining stuff. What does that mean? It means we have to use an ice table. If stuff's remaining after equilibrium, it means an ice table is needed. So initial, change, end. So initially I have 0.35 of this, 0.4 of this, none of that, none of that. At the end I have 0.19, right? How'd I go from this to this? Minus 0.16. 0.4 minus 1.6 is plus 0.6 plus 0.6 gives you 1.6, 1.6. Now, all of these things are in moles. I'm solving for Kc. What's Kc for? Concentration. Luckily, they're nice. It's all in 1 liter. So everything divided by 1 gives the same numbers, right? If they were mean and had a different value for that, for volume, it would change our numbers up. Does that make sense? But luckily, it's the same. Now it's just products of reactants. So 0.16 squared, because these two things both play each other, same thing as saying that squared, times 0.19 times 0.24 gives you, okay. Does that make sense what I did? Okay.
Yes.
Gonna go a bit quicker now. Going a bit slower because the Chatier's principle is coming up, but these are the math parts of this. The Chatier's principle is very easy to go through. Okay, again, An equilibrium, the flask contain this. I'm not going to go over this problem because this problem is exactly like the last problem. We're going to use ice again. Figure it out. I'm going to go to number 9 because 9 is Le Chatelier's principle. I also have another YouTube video about that. Okay. So, when volume, whoa, get my thing, here we go. When you increase volume, that's the same thing, or it's going to favor the side with the what? Most moles of gas, right? Put gas right here. A decrease in volume favors the side, right, with the least. Hint, hint, wink, wink. Write this down. Write this down 5 seconds before you get the test, and as soon as the test starts, you guys get scratch paper, right? Write it down. That way you don't have to memorize it during the test. Also know this. Volume and pressure are opposites. So a decrease in pressure favors the side with the most, and an increase in pressure favors the sides with the least. Okay. So increasing pressure, right, would not change which the following. If you're increasing or decreasing volume or pressure, it's going to favor the side that basically has the same amount of moles in each side. How many moles of gas do I have on the product side? How many on the reactant side? Because 2 equals 2, right? If I increase, decrease volume, it won't affect that one. Does that kind of make sense? Okay. A lot of your tests have gone over chapter 15, most likely will be Le Chatelier's principle, because it's quick, it's heavily covered, and it confuses you guys sometimes. But once you understand Le Chatelier's principle, they're pretty much give me questions. They're pretty easy once you know what's being asked. So number 10. First off, let's deal with this guy right here. Does someone say my name?
Yeah,
Nope.
I did.
Oh, you did? What's up?
Okay. So what are you looking at for moles?
So look for the number of moles of gases, right? So
Okay.
there's 2 moles of gas on the product side, 4 moles of gas on the reactant side. That makes sense?
Uh-huh.
2 moles of gas on product side, 3 moles of gas. 2 moles, 3 moles. 2 moles, 1 mole. 2 moles, 2 moles. Does that make sense?
So do you want them to equal each other?
You want them to equal each other because what is number 9 is asking which of the following reaction would increasing pressure not change it, right? An increasing pressure or decreasing pressure or changing volume, right, affects the side with the least amount. So I'm asking you what, like, a given equation, which one would not be affected by a change in volume or pressure? It's going to be an equation where the moles of each equal each other.
Okay.
That kind of make sense?
Since it says not change, that's
Yep.
why we did equaling.
Yep. So this is not change. That make sense?
Yep. Thank you.
Of course. Okay. So, first off, are there any solids or liquids here? No. Always check that first. Second, what's the H stand for? Heat. Change in heat. If you have Langley or Dale, they're going to say change in enthalpy. I don't like change in enthalpy because guess what? Next exam, change in entropy is the same thing. If you have Dale who has an accent, you have Langley who talks very quickly. Entropy, enthalpy will sound very similar to each other very quickly, especially when they're in the exact same equation, right? It would be, yes. Yeah, but the problem is them saying together because delta G is equal to change in enthalpy minus change of enthalpy. Exactly. See, welcome to my life. Delta G is equal to the change in enthalpy minus the change in entropy. They're in the same problem. That's why I don't like entropy and enthalpy. I like change in heat energy instead. It means the same thing. And the H makes sense for heat. That's why I've been teaching you guys is heat the entire time. So change in heat. The change in heat is negative. Exothermic or endothermic? Exo, what's that mean? Heat's given off. What side of the is it on the reactant side or product side? It's on the product side, right? Because being released. So just type this, add in the positive H, or add H in there to let you guys know that heat's being released. Now it's part of the equation, right? So if I change heat at all, it's going to affect the heat on the equation. Whoops. What? Oh. Been a hot second since I've jumped onto Zoom. You don't do a lot of Zoom things anymore. Okay, so a decrease in partial pressure, right? What that basically means is I'm taking this stuff away. If I take CO2 away, CO2 goes down. My reactance goes down. How do I fix that? I shift towards the left to compensate, right? It's a balance. Whatever I do to one side, I do the exact opposite side. A decrease in the value equilibrium constant. If this goes down, right? How do I make that go back up? Make products go up, right? Oh, I misread the question. My bad. That's why you give me guys weird looks. We're talking about adding O2. So if I add O2, this side goes up, right? So products go up. K goes up, right? So what's going to happen? To compensate for this, CO2 would have to increase, right? Sorry about that. I misread the question. Going a little kind of brain dead right now. Only work for so many hours in a row. Okay. So an increase in O2 would cause the product side to increase. To compensate that, right? Reactants would increase to compensate for that, right? A is saying the opposite, right? C looks good to me, right? Oop. E is wrong because that's also a product, right? So between B and C, right? The issue why I'm not picking B is because this is the constant at equilibrium. Does the constant equilibrium change at all? What can change equilibrium? What's the one thing that changes equilibrium? Do I affect temperature at all? So that's why it can't be B. If I change temperature, B would be a correct answer, right? But since I'm not changing temperature, B cannot be the correct answer now. That leaves C. Does that make sense? Okay. Exact same equation down here. Exothermic, add temperature, right? So an increase in temperature. So if I increase temperature, right, I'm increasing the H value hypothetically on the product side. So product side's going to go up, right? If products go up, right, how do I compensate for that? But K goes up. How do I make K go back down to normal? I increase reactants, right? But what do I change? I change temperature, which means I have to change my equilibrium constant. So I want my constant to go down to compensate for that. Does that make sense? Yes? Zoomies?
Yes.
Start off with 21 of you, have 19. That's good. Okay. Why is it not D? Is D the answer? You guys have any key?
No.
No, it's B, right?
I have a question.
Okay. The reason why it's not D is because I'm increasing temperature, which means I'm increasing the product side, right? A decrease in CO2 would make the scales go even further the opposite, right? Because if I decrease products, I'm going to increase, if I decrease reactants, I'm increasing products, right? So I'm shifting the scale even further on the opposite side. That's not going to make it equal, Le Chatelier's principle.
I have a question.
I have an answer. What's up?
So if you're increasing the temperature and it's on the product side, why wouldn't the equilibrium constant be increased?
Why
since
would
your
it
product is
decrease? Because you're going to Le Chatelier's principle saying you're trying to get back into normal order, right? So heat right now is on the product side because it's exothermic, right? So I'm increasing H theoretically as I'm making heat part of the equation now. So that's going to increase the product side. To compensate for that, the reactant side would also increase, correct? Does that make sense so far?
So it's not asking you what would happen if the increase, I mean, it's not asking you what would happen if the temperature increases, it asks what happens after temperature increases.
Yes, what happens after
Like
temperature
after, not
increases?
during.
So how would Le Chatelier's principle react to an increase in temperature, right? So if product size increases, reactant has to increase as well to make it back into equalness, right? The issue is, since I'm playing with temperature, I'm going to deal with the equilibrium constant because that changes with pressure. Not pressure, sorry, with temperature, right? And since I increase product, my K value went up. To make it back to equal, I have to decrease my K value. So I'll see a decrease in my equilibrium constant to compensate for that. Does that make sense? Does that make sense?
Yes.
Yes, thank you.
Okay. If it doesn't make sense, let me know. I can spend more time on it. Okay. I want to maximize the amount of CO I make. Where is CO located? On the product side, right? It's also exothermic, so heat's also on the product side. So to maximize the amount of CO I make, do I want a high temperature or low temperature? What do you guys think? So if I increase temperature, reactants, products, if I make my products bigger, right, is that going to shift it towards the right or the left? Sorry, the left or the right? Sorry, left, right. Got confused for a second. If I increase my products, I'm shift towards the left. Do I want to do that? No, I want to shift towards the right. That's actually going to be low temperature, right? Treat heat like it's one of the other things. If I remove the heat, I have to shift to make it back up, right? So low temperature. Next up, pressure. So I memorize volume instead. So an increase in volume and decrease in volume. So side with most, side with least, decrease pressure, increase pressure. So how many moles are on this side of gas on the product side? How many moles on the reactant side? So what pressure would favor the least amount? Oh, sorry, the more amount, my bad. A decrease in pressure, right? That's why 12 is C. Does that make sense? You guys give me confused looks. Does that make sense or no? Okay. Trust me, just write this down as the test begins. It'll make your life so much more easier to memorizing this. So how does a catalyst affect equilibrium? The answer is A. A catalyst is just going to speed it up without changing anything. Makes it happen faster, but both directions, right? So it doesn't affect K at all. So B is wrong, C is wrong, D is wrong. I have no idea what E is even meaning. I don't know what that means, but A is correct. Okay. What's the following? If the following reaction to equilibrium in a closed vessel at a temperature, what effect would adding more hydrogen do to it? So if hydrogen were to increase, how would the reaction, how would it react? What would happen? If products increase, what happens to, what do reactants also have to do to meet up with it? Reactants also have to increase, right? So concentrations of CO in water would increase. Right? What's going to happen to CO2? Well, how do I make reactants go up? Products have to go down, right? It's at equilibrium, right? So that guy would decrease. That's why the answer is C. Reactants would increase, CO2 would decrease to counteract the increase of hydrogen. Does that kind of make sense? Okay. Again, this is like the seventh problem of Le Chatelier's principle we went over. Okay. Kc is equal to the forward reaction over the reverse reaction. Plug it in. Moving on. For the following action, we have this amount of stuff. So, a good way to know what we're doing with this is to plug these numbers in. So first off, look. Are they all, or do we see any solids or liquids here? No, they're all gases, right? So products over reactants, right? 0.6 over 0.1 times 0.15, right? Someone tell me what that is. What's 0.6 divided by 1.1 times 0.15? What does that equal? 0.9. 0.6 divided by 0.1 times 0.15. Make sure you put parentheses with yours. Don't do it all at once. It's 40. Make sense now? Okay. Make sure you guys do things step by step. It takes longer, it's more accurate. Okay. Here's my K value. Is that my K value? So what am I looking at? I'm looking at the relationship between K and C, right? K and Q. I want K to equal Q. Are they equal to each other? No. Which one's bigger? Q is much bigger. How do I make Q go down? Make it go to the left, right? Make more reactants, we'll make it go smaller. So, reaction was out of equilibrium. Reaction proceed to form more products. That's not true. We'll proceed to make more reactants. That's true. Okay. 17 is just asking what Kc is. So, Kc is equal to products over reactants, right? Are there any solids or liquids? No. D times C. That right there just means squared. A squared. B cubed. Does that make sense? Someone keeps getting kicked out. Okay, bye. But that's what you would do. It's always products over reactants, yes. Okay. Moving onwards, moving onwards. Okay. I'm going to skip 18 because you should be able to do this by yourself now. Hint, hint. That's why the Chartier's principle is heavily tested. It was probably heavily tested on you guys' quizzes, right? Okay. Of course. I'm going to go down to now the fun stuff. Chapter 16. Your guys' favorite, right? Acid and bases. You love this stuff. I know you guys do. Okay. So, do you guys talk about strong acid and strong bases in class yet? You guys give you a list to memorize? Memorize that list. Trust me, it makes life much easier. HCl, HBr, HClO4, HI, HNO3. What's the last one? H2SO4. There is one more. What's the last one? HNO3. Here's the 6 that I want you to memorize. Most likely I'll ask you one of these ones. 7th one. I don't know. What do you tell you the 7th one was? I was only taught 6. So I'll memorize 6. H what? HCl4? Okay. Okay, there you go. 7 strong acids then. How many bases were you taught? LiOH, NaOH, KOH. What else? CaOH. Okay. If it isn't one of those 7 strong acids you were taught, or one of the 5 strong bases you were taught, it's weak. Is it easier to memorize all the weak acid and weak bases, or just memorize the little amount of the other ones? Probably the little amount of the other ones, right? Save more brain space for other things. Okay. So, what makes what's special about strong acid, strong bases? What do they do? So do strong bases. Strong things dissociate 100%. What does that mean?
Makes X negligible.
Makes X negligible, that's true. But, for example, HNO3, when it breaks down, it's going to make only this stuff, right? So anything I put into this guy, I will get as my H variable, correct? That's much easier than what Ka has to do, right? So whatever your concentration is for your strong acid, that's also your concentration for your hydrogen concentration, hydronium concentration. That make sense? So if I have 0.208 concentration of hydrogen, how do I find pH given that number? Make sense? Because pH is equal to a negative log. I'm doing OH. So, were you guys talk about the square method at all, or no? We did a little bit in the last video, but I'll pull up here too for you guys. pH to H. I call this a square method. You don't like this?
It's too much.
It's too much. If you have hydrogen, you want to go to pH, you use this equation. If you want to go from pH to hydrogen, you use that equation. If you have hydrogen, you want to find the OH concentration, use this formula. Now I tell you guys to stay away from that formula. Why? You guys have a notorious habit of not putting parentheses where they need to go. And you will mess that up. I took it the long way around. Just get the right answer. pH to OH, OH to pH. POH to hydrogen, hydroxide, hydroxide to POH. Square method. You don't like that, just know what the formulas are then. That's how I look at the relationship between them at least. Okay, bye. It's still recording. Don't worry about it. Okay. Moving on. Cool, going over here now. Clear. So, pH is equal to the negative log of H. So just plug that number into the negative log and you'll get a pH. What pH would you get? 0.60. So, 0.682. Is it a high pH or low pH? Which indicates what? Strong acid, right? Because the lower your pH, the stronger your acid. Correct? What about a low POH? What's that indicate? A weak acid or a strong base. Make sure you know the difference between the two. Okay.
There was a question on the test. You need to do that. Like if you have a high pH and a low pH, what do you have?
If you have a high pH, have a high pH and a low POH, you have a strong base. There you go.
It was what, like, way more wordy the way Langley does it.
Yeah. The Cool. Thank you, Langley. Okay. What is the pH and POH given this? KOH, strong acid, strong base. Which one is it? KOH. Which one is it? Strong acid or strong base? Strong base. What do strong bases do? Dissociate 100%, which means whatever I just plug that into my OH, right? I have that much OH stuff. One second. Yep, still recording. Okay. Share the screen. There we go. Okay. So I have that much OH, right? So POH is equal to the negative log of OH. So the negative log of 0.025, I will be given what? 1.6. So which one of those is a POH of 1.6? B and E. I don't know what this negative stuff is. You can't really have a negative POH or a negative OH, pH. That doesn't make any sense, right? That would be a soup, like a mega acid, mega base. Those exist, but not for you guys. There are things that are so reactive they tend to blow up by looking at them. They tend to react, but you guys do not play with that stuff until you're actual graduate students. Hence why you gotta keep playing with salt water in lab, because they don't trust you enough. So to find pH, it's 14 minus POH. Does that make sense? Okay. If you have Ka, what's Ka always equal to? X squared over HA. The reason I say this is because you guys want to do an ice table every time? No. You guys hate ice tables, don't you? So, if you're talking about a Ka value, just know it's X squared over HA. Okay. You're given a Ka value, right? Plug it in. Let's change my color just so people can follow online. 0.3 times 10 to the negative 6 is equal to, I know. The next part I want you to know is that 0.9 is part of Hx, which is just HA. So x squared over 0.59. How do I solve for x? What do I do? Congrats. 0.59. Oh, multiply, not divide. Oof, bad. Brain fart. 0.59. 0.59. Cancel, cancel. And then we take the square root of that, and that will give us our x value. So 0.59. Well, technically, first I should do that. 7.3 times 10 to the negative 6 times 0.59. And then I'll take the square root of that number. I got an x value of 0.002. This is why with Ka and Kb, we can ignore the minus x value that's theoretically right there. Because is that even close to a whole number? That's pretty small. In reality, that's pretty big for an H concentration, right? Even that's considered big is a small number, right? So to save us from doing the quadratic formula, we can assume that x is negligible, right? Cool. Negative log of x or h, you'll be given there. And that'll give you the pH, which is 2.68. Does that make sense? Okay. Again, concentration of HOCl, weak acid or strong acid. It's weak. It's not one of the things. Also, you're given a Ka value. That's less than 1. Hint, hint, wink, wink. If your Ka value is less than 1, you're dealing with a weak acid. Okay. So Ka is equal to x squared over HA. So I'm looking at the concentration of this guy, which means I'm solving for HA now, right? Because it tells you what's the concentration of that. What's interesting is this has the exact same pH as that, HNO3. What's that? Strong acid. What do strong acids do? So if I want to figure out, something, right? Has the same pH as this, which means I'll have the exact same amount of hydrogens as that guy. Correct? Plug that into x, square it, right? Then divide by Ka. You'll get the answer. Yeah. Anyone else any questions about how to solve this one? Okay. If you do, watch the previous videos. It's just an overview. No, catalytic ionization, it's known X is negligible. Hint, X is always negligible with Ka. We won't make it the quadratic formula. That takes way too long. So it's just another Ka formula, right? Turn pH to H, then basically square it, divide by that number, you get Ka. The one's about 31 though, because 31's an interesting one. Percent ionization. What is a percent? Something out of 100, right? Something out of a whole. HA, which is just our general, our genetic, or not genetic, but generic weak acid, breaks down to H concentration and A minus concentration, right? So whatever I get here, for example, 0.14, right? I'll get some amount over here, and that will be my percentage, right? Because this right here is my whole. Since it's a weak acid, it won't be 100%, right? It's going to be less than 100%, theoretically speaking, right? So let's figure it out. So for that, we figure out what our H concentration is. Ka is equal to x squared over HA. Ka, HA, changing color, 3.5 times 10 to the negative 8th is equal to x squared over 0.14. 1.4 multiplied by that, cancel, 0.14, 3.5 times 10 to the negative 8th. Clear, times 1.4, take the square root of that number. So I got 4.9 times 10 to the negative 3, not negative 3, negative 9th. What's up? You not get 4.9 times 10 to the 9? Oh. Square root. X is equal to 7 times 10 to the negative 5th. Okay, percent 0.14 over 7 times 10 to the negative 5th times 100. What percentage is that? Correct. Is that less than 10%? Can we ignore X, theoretically speaking? Yes. This is why we can ignore X and make sure X is negligible. If you're given percent ionization, right? 5.7% is equal to, right, concentration of H, or same thing as saying that's technically X, the same thing, right? Over HA times 100. Are you given HA? Yes, you are. Plug that in. So 5.7 divided by 100 divided by HA, multiplied by HA will give you X, right? Boom, you can figure that out. You don't need the K, you don't even need the Ka value here, theoretically speaking, right? You're going to solve it by doing this. You don't want to do that. You still have Ka is equal to x squared over HA. You still solve for X this way too. There's two ways to go about this problem. You'll get the same answer both ways. Does that make sense? Okay. What's going on? Okay, I might just freaking make a text chat for you guys, just so I can just text you all at once when I tell you guys I'm doing this. Be so much easier than emailing 30 students. Yeah, but the problem, I have to be involved, and that's weird. So I'll be involved. We'll figure something out. After the exam, we'll figure something out. Okay, a monoprotic acid dissolves in water is 30% dissociated, and the product of the solution is this. What is the Ka value? This is percent ionization. If you're doing percent ionization, right? Percent ionization is equal to X over HA times 100, right? From this, from the pH, you can figure out the X concentration because base 10 to the negative pH will give you hydrogen concentration. Given that, you can figure out HA. Given HA and X, you can calculate the weak acid, because Ka is equal to X squared over HA. Does that make sense? Okay. I am quickly going through these things because I do want to go home. I do have to do a paper / project. It's weird. Kb is the exact same thing, but Kb is for acid. Sorry, Kb is for base. My bad. See, brain no work right now. X is always negligible. Right? Same thing. If you solve for this guy, you're solving for the OH. If you take the negative log of that, right, you'll get POH. You get POH, just subtract 14 to find the pH. Does that make sense? You guys want me to do this problem or no? Okay. I want you guys to avoid this, where H plus is equal to 1.10 to the negative 14th over OH. I want you guys to avoid that, because you guys just proved to me today, multiple of you have a hard time plugging in those exponents like that. All right? It's going to take a bit longer to go the roundabout way, but you'll get the right answer. If you are confident putting this in with parentheses, you can do so, and you'll save yourself so much time, but you have a higher chance of getting it wrong. So do what you think is best. Oh, bad. Oh, well. Solve for OH, right? Find POH minus 14. 37. Calcium hydroxide is the pH of this. What is the concentration of that? You can just figure it out. Calcium hydroxide technically is a strong base. That is this thing, right? So if you figure out the POH, take 10 to the negative POH to get the OH concentration, you should be able to figure out to get this too. Kind of makes some sense? Okay. Okay, I know this one like this popped up in the test. But I'm gonna go do a better one because I like a better one down here. Talk about conjugate acids and conjugate bases. Let's talk about 34. This will help us solve the one we just kind of skipped over, I know. So what makes an acid an acid? Donates a proton, right? So this guy and this guy. Which one lost a proton? Which one gained a proton? When comparing it to so which one's the acid? Water is the acid then, right? That makes this one the base. Hint, hint, wink, wink. Acid and bases are always reactants. Hint, hint, wink, wink. So, C and E are wrong. Okay. Products are always conjugates of that, right? There are multiple ways of doing this. The way I like to look at it, think about it by itself. Which one will donate a hydrogen? Which one will accept a hydrogen? This one will donate the hydrogen, right? So that's the acid. That's the base, correct? Just put a C in front of it. Does that make sense? That's how I like to look about it. You guys are probably taught in class is that the base becomes the conjugate acid and the acid becomes a conjugate base, correct? That's true. You can think about it like that. But the problem is the more steps it takes you guys to memorize something, the more likelihood you guys will mess it up given an exam or quiz. And you guys are freaking out for an answer, right? If you know that an acid will donate a hydrogen, just look at which one donates a hydrogen. On the product side, just put a C next to it. It works the same way. Less steps are involved. Much easier, in my opinion. That makes sense? Because I guarantee you, during quiz or exam time, you're gonna have a brain fart, head's gonna start going blank, you're gonna start freaking out, and you're gonna forget which one the conjugate acid becomes, which one the conjugate base becomes. Do that instead. It makes life so much easier, trust me. So, which one is not a conjugate acid-base pair? So you're not even given what happens, right? But you can tell based on if they're an acid and base related to each other. If I take away a hydrogen from PO4, does it become PO4? So HPO4 becomes PO4 if I remove the hydrogen, right? Acid and base relationship. Looks good to me, right? Well, here, did one lose a hydrogen, one gain a hydrogen? Did one lose a hydrogen, gain a hydrogen? Did one lose a hydrogen, gain a hydrogen? Did one lose a hydrogen, gain a hydrogen? No, one lost 2 hydrogens. You cannot lose 2 hydrogen at once. You lose 1 hydrogen at a time. Diprotic acids have 2 hydrogens. Triprotic acids have 3 hydrogens. The amount of hydrogens you have, the amount of Kas you have. Dun, 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 multiple Kas. That's not good. You only usually care about Ka1 because it's so much bigger than Ka2. If you look at Ka2 and Ka3s, sometimes are like times 10 to the negative 20th or 30th. Very small number. It probably has no bearing on anything at all, right? So it doesn't really react very much. Okay. To figure out 39, we did it on my last YouTube video, but you make them all basic. So you make them all POH, right? Or all pH, and figure out which one is corresponding to. If you make it all POH, pick the smallest one. Make them all pH, pick the highest one. H2PO4, right? H3PO, right? One's an acid, one's a base. You're gonna use Ka1 for this because I only lost 1 of the hydrogens, right? H3PO4, strong acid or weak acid? It's weak. So you're gonna use Ka, right? Ka is equal to x squared over HA. Here's your Ka you use. Here's your HA. Figure out what X is, and there you go. You got your answer. Cool. Well, they usually are so small they don't matter, but also you're only looking at losing of 1 hydrogen. That's why I use Ka1. If it was a strong acid, you just would have plugged that in, figure it out. Yeah. Yep. There is only 1 strong acid you guys need to know about that is diprotic, and that is sulfuric acid, H2SO4. It's the only strong acid you know that's diprotic. The rest of them are monoprotic. Okay. So the higher Ka value indicates what? Stronger acid or weaker acid? If Ka goes up, that's going to indicate what? More hydrogens, right? More hydrogens indicate what? Stronger acid. So higher Kas indicate a stronger acid. HOCl, right, has a Ka of 3.5 times 10 to the negative 8th. Hydrofluoric acid has 7.2 times 10 to the negative 4th. Which one is bigger? hydrofluoric, right? So this is a stronger acid than this guy, right? The stronger acid will win, even though technically it's a weak acid. It is stronger, right? Acids don't want to exist. It's going to shift it that way, right? If you shift it the other way, K, products of a reactant, I'm going to make more products and more reactants. Going to make more reactants, which makes K less than 1. Does that make sense? Look at the Ka values. The bigger one indicates a stronger acid. The stronger acid doesn't want to exist. That's what happens. Okay. So Ka is greater than 1, which means we're going to make tons of products, right? Good, which indicates we're going to make tons of products. Looking at the reactants, which one's the acid? Which one's the base? That's the acid. That's the base. Looking at the reactants, which one's the acid? Which one's the base? This is the acid. This is the base, right? I know that because this guy will donate its H to make this guy again. Kind of make some sense? Okay. If K is greater than 1, well, I mean, I'll make more products than reactants, right? So the reactant's acid is much stronger, correct? Good. What about bases? Which base is stronger? So is the reactant's base. A stronger base will pull hydrogens more easily, right? If this base was stronger, if their product's base was stronger than the reactant's base, it could actually make the weaker acid technically stronger because it can pull its acid. Kind of makes sense? Thus lowering the concentration, thus driving reactant forward. The stronger acid is your H2CO3. Boop, boop. Which one's the weaker base? And that's why the answer is E, because that's the weaker base. Does that make sense? Okay. Whoops. HNO3. Strong or weak? So it's 100%, right? Strong acid, so it's 100%. So if I increase this, is there equilibrium here? Yes or no? Do strong acids, strong acids and strong bases that have equilibrium? Yes or no? No. They associate 100%, right? Which means anytime I have any of this, it'll be immediately broken down to that. It can never overcome how strong the acid is, right? So equilibrium cannot be maintained or equaled. You can theoretically do it, hypothetically. It just takes a ton of energy to make it happen. It's usually not worth it. So if I increase the concentration of the acid, what happens? Nothing. It can't go backwards, right? So, sorry, my bad. I messed with the question. So, yeah, so this guy increases, right? What's going to happen? Concentration of H is going to go up. Concentration of that's going to go up. Does that make sense? It's a strong acid. As soon as I get one of these molecules going, it immediately breaks down. Correct? So what's going to happen to the H? Tell me it's going to go up, right? H concentration is the same thing as HO3 because of dissociation of water. It pretty much is the same thing. So what happens? It increases, right? So C and D are wrong. If H plus goes up, what happens to O minus? Goes up or down? Goes down. So a strong acid has a lower pH or higher pH? So which one's going to be? pH is going to go what? pH is going to go down. All right, because as your concentration of hydrogen goes up, pH goes down. It's weird to think about, but that's how you do it. That makes sense. Okay. Or in 44, or in 50 theoretically. With 46, you're basically going to make them all POH, figure it out. 47, decreasing base acidity. So, how do you tell if someone's a strong acid, given Ka? Bigger Ka means what? Which one is the biggest Ka value? So that should be our first one, right? Because we're decreasing order. Okay, what's the next one? There's 1. What's next? What's second strongest? Good. What's next? What's next? What's next? Which one's 1, 2, 3, 4? B. That makes sense? Okay. 48, just basically asking as concentration of A goes up, what happens? We already talked about this. Okay, let's talk about 49 and 50. Apparently a question like 49 was popped up in your guys' quiz, right? Okay, let's talk about it. I didn't think they would ask you about that. That's kind of stupid. So a basic salt, a basic solution. So when a strong acid and a strong base interact, right? What type of solution does it make? Makes neutral. When a strong acid relates to a weak base, it's going to make an acidic solution. When a weak acid and a strong base interact, what type of solution does it make? Makes a basic solution. So I got to figure out which one of these is going to be a weak acid reacting with a strong base. Does that make sense? So let's just add H's and OH's to things and figure out what's going on. So HBr plus NaOH, strong or weak? HBr, strong or weak? NaOH, strong or weak? So strong acid, strong base gives you what? Neutral, wrong. Okay. HNO3, strong or weak? Strong. KaOH, strong or weak? Strong. Neutral. HCl plus ammonia, strong or weak? Weak. Gives you acidic. Is that what I want? No, I want basic. CH3COOH plus NaOH. This guy right here, what is it? Weak or strong? Weak acid. That's how you do it. You break apart the last part, which is usually the plus charges, right? Add OH to it. Find the thing with a negative charge, add an H to it. That should tell you what you're adding together. That's the best way of doing it. That kind of makes some sense? Okay. If you're given Ka and you want to solve for, if you want to get Kb, there is a way of doing this, and that is Kw. Kw is equal to Ka times Kb. What does Kw equal? The ionization of water, which is 1 times 10 to the negative 14th. So 6.2 times 10 to the negative 10th times Kb. Kb is equal to 1 times 10 to the negative 14th whoops, 6.2 times 10 to the negative 10th. Figure it out, solve it, get the answer. The answer is C. Here you guys go. Ta-da! It only took us 3 hours. Woohoo! Yeah, but I skipped a lot of them. Okay. Was that helpful? Okay. Does anyone have any questions for me? Anyone at all?
Oh, I have a question, but it's like related to a lab.
Okay.
I don't understand. Like, it was the equilibrium lab.
I'm gonna make a YouTube video about Equilibrium Lab later on.
I'm
So
from
you
like
can
a
watch
different
that one for me. What?
class.
Say,
I'm from like
sorry.
I'm from a different class, so I don't get the benefits of having a great teacher like you. So
When is it due for you?
it was due last Sunday, but I can't figure it out. And my teacher told me to do something, and it still didn't help me.
Okay. So with Equilibrium Lab, do I have access to my stuff? One second. Let's see if I have access to my stuff. I had to post stuff. My CHM-115 bus. Okay. I'm going to make sure I stop recording this.